Okay, let's go ahead and get started. I hope everyone had a good weekend. So just to start off with a couple of announcements, the midterm is ongoing and due Wednesday before class in grade scope. I did give like a buffer hour in case there's like any last minute technological difficulties. But the deadline is firm, so please turn it in on time. Bean. The second announcement is that there won't be office hours today, and I will, so once the midterm is over, I'll make office hours for the term paper for like the time between, Wednesday and whenever the term paper is due. And Wednesday is our last lecture. Okay, are there questions about any of that? Okay, so last class we saw a theorem that said when p of x is a polynomial with coefficients in some field, that p of x is irreducible if and only if f of x mod the ideal generated by p of x is a field. Okay, and then you had some exercises about that, and I posted the solutions to those in Canvas if you want to have a look. So this sort of theorem motivates us to make the following definition. So we'll say a field E is an extension field of a field F if F is contained in E and the operations on F are the same. So, and the operations of F are the ones in E, just restricted to F. Okay, does the definition make sense? Yeah, question? So if I'm in E and I do, like, for example, E addition or E multiplication of two elements that are actually elements of F, that's the same thing as if I did the F multiplication or F addition.
What if the elements are not F, but are E?
Then that's fine. Then, yeah. It just has to be a field. Yeah. Other questions? Okay, so some examples using fields that we have seen. So the complex numbers are an extension field of the real numbers. They're also an extension of the rational numbers. R is an extension of the rational numbers. And then an example from the exercises. This field, so we know this is a field from the theorem from last time, is an extension of the field Z mod 2. Okay, are there any questions about the definition or the examples? Yeah. C is an extension of Q, because Q is like inside of C. Of Z, no, because Z isn't a field. Yeah. Yeah, other questions? Okay, so we're going to prove a theorem. So we've seen before that the complex numbers is isomorphic to Rx mod x squared plus 1. So this may make you wonder, if you have a polynomial and it does not contain roots in the field that you've defined it over, is there an extension field where it does have roots? And the answer is yes. So that's the statement of this theorem. So let's let F be a field. And let's let f of x be a polynomial with coefficients over f, and we want it to be non-constant. Okay, then there exists an extension field E of f in which f of x has a root. Okay, so this is the theorem that we're going to prove today. Are there any questions about this statement before we jump into the proof? Okay, so let's prove this. So a priori, we don't know that f is irreducible, and we know that we can only make fields out of irreducible polynomials. So the first step is going to be to let p of x be an irreducible factor of f. Is it clear that this p of x exists? Or should we say more? So maybe I'll say a few sentences. So let's say f is reducible and we factor it. Then it factors into two polynomials of lower degree. If those are then reducible as well, factor them again, and just keep doing this. You know it has to stop somewhere because they all will have positive degree, and the degree of f is finite. So kind of worst case scenario would be that it fully factors into linear factors, and you have degree f many of them, and those are your irreducibles. But if it's, if it doesn't have linear factors, or if it doesn't factor completely into linear factors, then you will have some irreducible factor. Okay, is it okay? Yeah. Okay, so then it's enough to show that there is an extension field E in which p of x has a 0. So we construct an E where p of x has a 0. So what should E be? Yeah. No. What should E be? Yeah. Yeah, so let's try this one. So let's take fx mod the ideal generated by px. Okay, so from the theorem from last time, we know that this is a field because P is irreducible. Okay, so it is a field. So we need to show that it contains F, right? We want this to be an extension field of F. So we want it to contain F. And then we also need to show that P of X has a root in this field. Okay, so let's show first that it contains the field F. So consider the map. Phi from F to E, which just sends an element A in F to the element A plus the ideal generated by Px. Right, so that's in this coset is an element of this factor ring. Okay, so I claim, but I'm not going to prove, that this map will preserve the operations and is one-to-one. So that means that phi will be an isomorphism onto its image. And so that sort of means that, so what is in phi f, so this is going to be everything of the form A plus the ideal generated by Px for A and F. So we can view this as being the field F sitting inside of E. Does that make sense? Yeah.
So F doesn't need to be a subset of E, it just needs to be isomorphic to a subset of E?
Yeah. Yeah, so often, because of this, a lot of times you'll see the element A plus the ideal generated by Px just represented as A inside of the extension field E. So you just identify those two things. Okay, so then we need to show that the last thing that we need to show is that P of X has a root. In E. Do we have a candidate for what the root should be? So I guess from our experience in working with these things, we know that in fx mod px, how does like the algebra in this ring work? It acts like P of X is equal to 0, right? So thinking back to the example x squared plus 1, in Rx mod x squared plus 1. This, whenever you like multiply or add elements, everything acts as though x squared plus 1 is equal to 0, or in other words, it acts as though x is equal to I. So in this setting, x is acting as a root of this polynomial. So we're going to show that the element x plus, whoa, I don't know what just happened. We're going to show that the element x plus px is a root of px. Does it make sense? Like why this is what we believe might be a root? Okay, so let's write px as like a sub n, x to the n, plus, I'll go down to like a2 x squared plus a1x plus a0. Okay, so let's suppose that this is how our expression for p. Then let's plug in the coset x plus px. Okay, so what happens? We get an times x plus px to the n, and so on down to a2 x plus px squared plus a1 x plus px, oh my gosh, plus a0. Okay, yeah, let me just comment quickly. So like where is all of this taking place? So p has the coefficients of p live in f, but now we're plugging in something from e. So all of these operations are going to be taking place in e. So we're kind of conflating this number, which is an element of f, with the corresponding element in e. So I'm not going to write this out as an plus px, but that's like really what it is. Okay, so let's expand this out. So in e, right, how do we multiply cosets, or how do we take powers of cosets? We'll just take the power of the coset representative. So this will be an times x to the n plus the ideal generated by px plus a2 x squared plus px. Oh, I put my lines too close together. Plus a1 x px plus a0. Okay, so then we can bring these coefficients in and then also add up all of our px's. So this will become an x to the n plus down to a2x squared plus a1x plus a0 plus px. Okay, does that step make sense? So I kind of did more than one thing at a time. I multiplied these, and then I also added all of the cosets together. Okay, but then what do we have? This is px. So it just gets absorbed into this ideal. So we have the 0 element in E. So E has a root of px. So then it also has a root of our original polynomial f, because p was just a factor of f. So that completes the proof. Okay, are there questions about the proof? Yeah.
For the first part, you explain it how f is root where f is contained in E.
Yeah, so we're viewing, so in E, right, everything is cosets. So I'm going to view the element, which is of the form something in F plus this ideal as the corresponding element in F. And maybe there's something to check that is like 1-to-1. So no, if you take separate elements of F, then they don't get identified with the same element. Yeah. Other questions? Yeah.
So we showed that P of X has a solution in E, right?
Yeah.
How does that prove that F of X has a root in E?
Yeah, okay, so we showed that P of X has a root in E, right?
P of X is a factor.
And P of X is a factor of F. Mm-hmm. Yeah.
So show that there's only like 1 0. If f of x has multiple zeros, it's not necessarily that all of them are equal.
Right, yeah, it could be, yeah, exactly. There could be, you might need to take like multiple extensions. Yeah. Okay, other questions? Yeah.
So do you already have a polynomial field and you want to like get an extension of that algebra, or you kind of like make a new polynomial in like a different variable or something?
Yeah. Yeah, so if you wanted to take like another extension, like we're gonna call, so like say f factored is 2 irreducibles, and we took one, p of x, and created this field, but we want it to factor, we want the other one to also have a root, then you'd take a polynomial ring with these coefficients and then mod up by the other one. Yeah. Yeah, question?
So wait, P of X is that like an element of E?
P of x is an element of fx.
But like, how come it's another root in E if it's not an element of E?
Okay, so yeah. So P of x is an element of fx, and we're viewing f as a subset of E. So in that way, it's also a polynomial with coefficients in ex. And I guess now the variables are getting confusing, so maybe we should think of E as really being like fy mod py, something like that. Yeah. Okay, if there's no other questions, then here are the exercises. So let me make a comment about this. So this problem I found to be quite hard. So if you're working on it, let me know if you like. Well, I mean, if you're working on any of them and you have questions, let me know. But this one I thought especially was kind of difficult. And so go ahead and split up and work on these problems, and then I'll circulate and see if there's any questions.